Hello, this is Christiana once again, and today I'll be covering the topic of conjugated compounds and UV spectroscopy. Depending on what textbook you use, this may be a different chapter, but for the McMurray ninth edition organic chemistry book, it is chapter 14. So let's go ahead and get started. So the first concept that we must cover for this chapter is the concept of conjugation. The concept of conjugation basically follows that when you have three or more atoms that have the ability to resonate, and are adjacent to each other, okay? So, if you repeat that, it says when you have three or more atoms that have the ability to resonate and are adjacent to each other, that's when you can have conjugation. So, what do I mean when I say adjacent? I basically mean when they are one carbon away from each other, right? So, um, we talked about resonance in organic chemistry 1. Resonance is when you have a compound that is able to distribute its electrons or its charge throughout the structure, because it's either you have like a pi bond, a lone pair, a radical, a cation that will be stabilized by being delocalized or being distributed. Okay, so another note here that you should know is that when you have higher conjugation, this will produce a higher UV wavelength uh, for UVV's spectroscopy, which we won't really go over in depth in this particular chapter. Okay, so like I stated before, your compound will be able to resonate. Let's put that in purple. Compound will be able to resonate when it has pi bonds, lone pairs, radicals, cation, which is a positive charge, radical, which is a one electron in the orbital, lone pairs, two electron in the orbital. Pi bonds will be your double bonds and your triple bond. And with lone pair, you can also consider, mostly for carbon, it's gonna have a negative charge. Okay, so let's basically look at an example where something is able to experience conjugation, right? So if you have something that looks like, let me use this one. If you have something that looks like this, we know it will be able to resonate, will be able to experience conjugation, because first we see that I meant to change this one. Okay, first we see that this right here can resonate, right? And this right here can also resonate. Um, so you have, so our criteria to for conjugation is that you have three different atoms that are adjacent to each other that are able to resonate. So if we look at this, you have carbon 1, you have carbon 2, and you have carbon 3, right? Um, so this, you can see that the pi bond is between carbon 1 and 2, and uh, the positive charge is on carbon 3, and they are adjacent to each other. They are one carbon away from each other. So yes, this does meet the criteria for conjugation. Okay, another case would be if you have something that looks like, uh, let's see, like that, right? Um, why would this meet the criteria? So you have 1, 2, 3, 4. So on this 4 carbon, you have a pi bond, and they are at least, I mean, they're 1 carbon away from each other. So this is able to also experience conjugation. All right. So now that we are basically uh, more familiar with the concept of conjugation, let's talk about allylic carbocations, anions, and radicals. So yeah, you may have seen that I already pre wrote the notes, and this is because my recording keeps cutting off and playing without sound, so I do apologize for that. So basically this is just an overview of resonance. So with resonance, when you have a positive charge that's resonating, it's going to basically, so you remember your electron is always going to move from a higher electron density to a lower electron density. So your arrow is going to be moving, is going to be moving from the double bond, right? The double bond, which is, I'm referring to this one right here. The double bond, the arrow is going to be moving from there, and it's going to be moving towards the carbon where there's a positive charge. And basically what happens is that the positive charge will switch places with the pi bond, right? Whereas for your anion, so your uh, lone pair, right, is your place with the high electron density, right? Because you have a full negative charge on that carbon, right? So the electron is going to be moving towards the area of low density, right? Low electron density. And because once you create another bond there, that carbon with the green dot is going to have too many bonds, right? Carbon likes to have 4 bonds. That carbon is going to have way too many. So we're going to have to break that bond. And basically this causes the double charge to be on the side where the double bond was, and the pi bond will now be on the side where the negative charge was. So similarly with the radical, however, keep in mind that when you have a radical, that means you have 1 electron that's hanging out. So it's not 2 electrons. So you cannot show the mechanism with a full arrow. It has to be a fish hook arrow. Okay, so fish hook arrows. with that, you're going to have three different bonds, right? First, you're going to have this, an arrow coming off of the official arrow coming off of the radical, because that's the place of a high electron density. And then you're going to have this artificial arrow coming from the that side of the double bond to form a new bond, right? To form a new bond. And then the other electron, because remember this pi bond is representative of two electrons, right? There's going to be one electron left after that happens, right? And that electron will, just one electron will have to be on that carbon. It's going to remain on that carbon. So this shows that the one electron, the radical, is going to be left on that carbon, while we have that new bond that formed between the second and the third carbon. Okay, so yeah, that is the general overview of how of allylic carbocations, anions, and radicals, how they how they resonate. Okay, so let's go over the concept of how carbocations are, how the trend of their stability, right? If you recall, the tertiary is our most stable, while primary is our least stable. Tertiary meaning the carbon is connected to three other carbons, while and this is for a carbocation, right? So forgot to put the charge. So this is for a carbocation. So it's gonna be more stable if it's tertiary, and least stable when it's primary. So where do conjugated compounds, where do they fit in that trend? Conjugated allylic conjugated allylic carbocation. So the allylic, this is allylic and this is benzylic. Okay, so allylic and benzylic carbocations are actually going to be more stable than the primary and the secondary carbocation. However, they will be less stable than the tertiary. Okay, so it's a similar case for your radicals. However, the still we have that the tertiary is the most stable, while our primary is the least stable. But when it comes to the allylic and benzylic trend, they are actually more stable than the tertiary for a radical. Okay, so that's the only minor difference. But in both cases, we see that the conjugation is still going to increase the overall trend for carbocation or the radical. Okay, so let me bring back a reaction that we are familiar with from orgo 1, halogenation, right? Halogenation is when you react alkene, right? This is our alkene. You react it with a dihalide, right? Or halogen, you react it, and in that case, I'm so sorry, I keep pausing, I'm trying to look at something, I'm so sorry. Okay, so basically our product for that reaction, if you can recall, is that we will get a vicinal dihalide, where your products will be trans to each other, right? So now in this chapter we'll talk about something called allylic halogenation. The difference is that you see in this example we have nothing, just all we have is the dihalide, right? But for allylic halogenation, you're going to need a radical initiator, right? That will either be light or your NBS, right? That NBS is a source of bromine. All right, you're going to need a initiator like that. So you're going to go through the process of initiation, propagation, and termination. That is another topic that was covered in Orgo 1. If you want a video on that, let me know. I may have another video on that, or send you a link to a good video that explains the process. But yeah, the main things is that during initiation um you produce two radicals from your uh dihalide or your diatomic halogen, and your propagation step will focus on producing the reproducing the radical halogen, right? And your allylic acute halide, right? Your termination step will show how basically all the possible radicals come to bond together. So your two um, halogen radicals will come together to form the diatomic halogen, and then the major product will come from your radical, your uh, alkane radical, and your halogen radical coming together to form an allylic acute halide for this allylic halogenation. Halogenation. So, and then this is also a minor product, but you still have that 2R group, 2R radicals that will come together to form, those two bonded together. But the major one that we are focused on is where the R radical, your carbon chain radical and your halogen radical will come together to form an allylic acute halide. So, just going back on the differences, the for halogenation you produce vicinal dihalides. For allylic halogenation you produce allylic acute halide. Okay, I hope this video was helpful. This is part 1 of chapter 14. Tune in for part 2. I hope to see you again in the next video. Thank you so much for watching, and have a wonderful day.